Okay, thank you everyone for coming. So now Rudradip Biswas is going to talk us about generation properties of triangulated categories using cohomological or homotopical invariants. Okay, thank you very much, Rudradip.
Yeah, thank you very much for the opportunity. I have to thank Noe for that especially, and also thank you as well for the invitation. So today I'll be talking to you guys about some triangulated categories that arise in the study of representation theory. So two such categories that I'll be dealing with are the derived unbounded category of, let's say, chain complexes of modules over group algebra. So I'll be dealing with groups, you will see, group algebras with the groups belonging to a special family, let's say, or hierarchy. I'll define everything in detail shortly, of course. And the other triangulated category that I'll be dealing with will be sort of a small stable module category, small stable module category of modules that satisfy satisfying a finiteness property with all modules being taken over group algebras again. Being taken over group algebras where the groups again come from a hierarchy, and we're talking about the group still, and satisfy a cohomological finiteness condition. So these groups need not be finite groups. So derived unbounded categories are fairly common in representation theory, and I'm guessing almost everyone in the audience is fairly used to dealing with derived categories in general. So when I say derived unbounded categories of chain complexes of modules over group algebras, so like there is nothing in that phrase that is going to intimidate anyone, at least in this audience, I'm sure. Now, stable module categories usually are studied over finite groups. So usually we study stable module categories of Kg modules, where K is a field of characteristic P that divides the order of the finite group G. And there has been a lot of work, of course, over the past few decades now by people like David Benson, Srikant Iyengar, Henning Krause, Julia Pevsova, and actually going back, Eric Friedlander and a few other people, where they have studied these stable module categories as triangulate categories with co-products, and they have classified all the localizing subcategories, all the co-localizing subcategories, all the thick subcategories, etc., of these stable module categories. So today, we will be dealing with stable module categories of infinite groups, but not just the big stable module category, the small stable module category. So again, when we talk about small stable module categories for finite groups, it is usually taken to be understood that we are talking about finitely generated modules. So in this talk today, you will see that we are not talking about just finitely generated modules, we're talking about something slightly more general. So before getting there, as promised in the abstract, let me talk about a few invariants. So when I say invariants, I mean cohomological invariants, of course. Okay, so when did I begin? Did I begin at 8 past or?
Yes.
8 past, yeah, let's assume 8 past. So we'll stop at 58 past. Okay, so cohomological invariance of, again, infinite groups, but I'm just going to write groups. So the theme of this talk is I will introduce some invariants. I'll talk about their behavior, their usefulness, and some of their properties, and then show how the behavior of these invariants for some groups, as I keep saying, groups belonging to some hierarchy, which I'll define. So I'll show how the behavior of these invariants over groups belonging to some hierarchy dictates certain generation properties of the two triangulated categories that I've already mentioned. So what are the invariants that I want to deal with? So number one is an invariant called SILP. So what is SILP? So for any ring R, let's say R is a ring. I don't require R to be, okay, I'm not using the correct color. I want to use yellow for this. So SILP is for any ring R doesn't need to be commutative here, is the supremum over the, so look at the letters SILP, so supremum over the injective length of projectives. That's how the acronym SILP gets generated. So when it's injective length, I'm talking about the injective dimension. And the reason I'm saying length is because when these invariants were first introduced by two mathematicians called Gedrich and Grunberg, they used SILP and SPLI instead of SIDP and SPDI. So supremum over the injective dimension of all R projectives. I mean, P capital. I'm not just focusing on finitely generated modules. Similarly, SPLI means supremum over the projective dimension of all R injectives. Now, I'll shortly show why these are interesting invariants to think about. Then I have this other guy, which is basically a module, B gamma A. So where gamma is a group, any group, and A is a commutative ring. So what is this thing? So it is the module of all functions gamma to A with finite range. Again, you will see why this is useful. Number three is this thing called the Gorenstein cohomological dimension of a group gamma with respect to a commutative ring A. So what is this? Well, just like we define the normal cohomological dimension as the projective dimension of the trivial module, here I will be defining this as the Gorenstein projective dimension of the trivial module A. So what do I mean when I say Gorenstein projective? I'll define that in a second. For that, let me just write, this means Gorenstein projective dimension of the trivial A gamma module. So now I need to tell you what Gorenstein projectives are, because otherwise this doesn't make any sense. So what are Gorenstein projectives? Well, to get there, I need to give you one more definition, and that is the definition of a complete resolution. But I'm not going to use the word complete resolution. Instead, I'm going to take a shortcut and use the word totally acyclic. So what is a totally acyclic complex? So I'm guessing, again, many of you in the audience know this. The totally acyclic complex of R projectives is an acyclic complex of R projectives. Let's say for any ring R, of course, R doesn't need to be commutative here. So let's say this guy is P star, such that hom R P star to any projective guy, to any projective module is acyclic. So such complexes are called totally acyclic complexes. And Gorenstein projective modules. So Gorenstein projective modules are precisely, I'm giving you the definition now, precisely those modules that occur as kernels in totally acyclic. Totally acyclic complexes of projectives. So of course, I'm talking about R projectives for some fixed ring R. So when I'm talking about Gorenstein projective modules, I mean R Gorenstein projective modules or Gorenstein projective R modules, let's say. So now the thing is, well, I just mentioned the word complete resolution, the phrase complete resolution, and didn't do much with it. So complete resolutions, even though we won't be maybe using it too much, but as an idea, it is important to like just say what it is. So let's say I'm taking an R module, M has a complete resolution as an R module, let's say, I don't know, F star, if and only if F star is a totally acyclic complex of projectives, of course, and some high enough syzygy of M is a kernel in F star. I'm giving like the shortcut way of, I'm taking the shortcut route of defining complete resolutions. So when this R guy is a group algebra, let's say tau some group and a commutative ring. So when R is a gamma and A as an a gamma module admits a complete resolution, or let's say has a complete resolution, then that is the definition of saying the group gamma admits complete resolutions over A. The reason I'm saying all this is because later on, when I'll define or when I'll say how to construct stable module categories for infinite groups, the key criterion there will be that the infinite group that I'm dealing with must admit complete resolutions. So I'll just make a small, let's say, I don't know, detour, important for later. Well, this is a result mainly due to Matza and Simmons, Nadia Matza and Peter Simons. I don't know why I said Simmons. He was my PhD supervisor. I should say Simons. So they construct, so we can construct stable module categories. I'll give you guys their definition later of a gamma modules where A is a commutative ring of finite global dimension. So global dimension means supremum over the projective dimension of all modules, and gamma admits complete resolutions over A. Actually, I mean, if you go and read their paper, you will see that this is not what they do. They require gamma to satisfy certain properties that are slightly stronger than, say, gamma admits complete resolutions. And they require A to be Noetherian. But it turns out that their treatment works perfectly well for this situation. So now, where were we? So we were talking about complete resolutions, and before that, we were talking about Gorenstein projectives. And before that, we were talking about this guy. So when I talk about the Gorenstein cohomological dimension of a group, I'm talking about the Gorenstein projective dimension of the trivial module. So Gorenstein projective dimension, once you know what Gorenstein projectives are, is straightforward. Like it is the length of the minimal length of a resolution of your module by Gorenstein projectives. It's just the way dimensions are defined in homological algebra. So I've introduced Silp-Splee, then this module B gamma A. So here the invariant is the projective dimension of this module B gamma A as an A gamma module. And I've talked about GCD. I want to talk about another invariant. So invariance continued. I'm going to talk about two more invariants, sorry. So one is the finitistic dimension for any ring. Again, this is quite common. So this is the supremum over the projective dimension of all R modules. Again, note that R doesn't need to be commutative. R doesn't need to be anything. Any ring is fine. Supremum over the projective dimension of all R modules that have finite projective dimension. I mean, as R modules. This is a very widely studied quantity in representation theory. And finally, I have this guy, K. So K A gamma. So gamma is a group and A is a commutative ring. So Ka gamma is defined to be the supremum over the projective dimension of all A gamma modules that have finite projective dimension, not as A gamma modules, but when restricted to finite subgroups of gamma. So you take an A gamma module M, you can think of your M as an AG module, let's say, where G is a subgroup. So now let's say G is a finite subgroup, and I'm looking at the projective dimension of M as an AG module over all finite subgroups. Of gamma. Right. So these are some invariants. So Findim K, and from before we have Silp-Splee, this guy, projective dimension of this guy, and GCD. So now how are they connected? And what is the usefulness of all these things? So I'll just talk about a couple of usefulness, and then I'll go straight to one of my new results, which deals with the way they are all connected to each other. But of course, that result didn't come out of vacuum, like it developed on results that already existed in the literature. So some usefulness, well, it is known that if Silp and Splee are both finite, then, and only then, if and only if, all R modules have complete resolutions. I've already talked about what complete resolutions mean. We have complete resolutions. Then for a long time, this was the best known result that we had. So let's take A gamma again. So now A is a commutative ring of finite global dimension T, and gamma is a group. Then this was a result that SILP of A gamma, like supremum with injective lens, is bounded above by this guy. So both these results are from the paper by Gedrich and Grunberg, where they first introduced these things. I believe it's 1986. Sadly, both of them are dead now. Right, okay. And one other result that is sort of important here is that the B gamma guy, B gamma A, remember this? So it turns out B gamma A is A free. It's free as an A module. And this is actually quite a deep result. It goes back at least like 30, 40 years. But in its modern incarnation, it is due to Benson, David Benson. '97, I want to say. And also B gamma A is AG free for all finite subgroups G of gamma. So again, both of these results are due to Benson, but it's questionable as to whether or not like he brought them out of vacuum or they existed in some form or the other in the literature for like a much longer time. And the reason why B gamma A was interesting to Benson in this paper, so this paper is, if you want to look it up, it's a very interesting paper. It's called Complexity and Varieties for Infinite Groups. There is a 1 and a 2. Both of them are in the Journal of Algebra, 97. So the reason why it was interesting to him was so Benson was putting a closed model category structure on, say, the module category A gamma. So I don't think I need any conditions on A gamma yet. But well, you can force some nice conditions on gamma, but that's not important for us in this talk. And it turned out that when you do this, like you can do it in such a way such that the homotopy category is equivalent to the stable module category. Like writing star mod for stable module category means that, I don't know, we're using the notation used for finite groups. So I'm just going to write the stable module category. Which stable module category, etc., we'll like talk about that in a minute. And like the cofibrant objects he showed were given by those modules such that, or for which M tensor B gamma A was projective. So these modules are called, this is a definition now. So a module M such that M tensor B gamma is projective are called cofibrants, but since I'm not dealing with model categories in my talk or in my work, I call them Benson's cofibrants. And it is a conjecture still open. This conjecture is due to Olympia Teleli, and I think one of her students, Dembe Giotti or Giotti, I don't know, like what the correct pronunciation should be. It's a Greek name, of course, 2010. So the conjecture is that for any group gamma. And so, well, they made the conjecture over just gamma. I made it over commutative rings of finite global dimension. So maybe I should also put mine in there. 21. For any group gamma and any commutative ring A of finite global dimension, Gorenstein projectives. So Gorenstein projective A gamma modules, this class should be exactly equal to the class of Benson's cofibrons. Since it's not on the screen, I'm going to write it out. So it means all modules M such that M tensor B gamma A is projective. And the thing is, this is a very useful and handy conjecture. The reason being that Gorenstein projective modules often are not very easy to handle, in the sense that it is not very easy to characterize them completely in many cases. Whereas when you're talking about all modules M such that M tensor specific module is projective, that category is somewhat easier to handle from all sorts of perspectives. Like if you're thinking about computing these modules, I don't know, in Magma or some other coding language, then this class is easier to deal with, I guess. And also for all sorts of homological tricks, like if you're tensoring with something that is A free, then lots of things are preserved. B gamma A is A free, as I just mentioned. So there's a light over here. It's getting a bit. Just a minute, I'll turn on the lights. Right, so now the reason I bring this conjecture up is because, well, let's call this conjecture A. I'll show why conjecture A is actually related to the behavior of some invariants. So I have given you a short overview of some results that we know about these invariants. And now let me go to a result, which is due to me, about how these invariants deal with each other, interact with each other. I turned on the light, but like my picture got hazier. Anyway, doesn't matter. So here's a theorem. I'm gonna say it's due to me, but of course it builds on work done like way before my time. And also, of course, this work was done in 2020. The paper came out in 2021, so I have to say 2021. So to get to this theorem, I want to, okay, no, let me just say it first. So for all gamma, oh, sorry. Let gamma belong to a class of groups. I'm not going to be vague anymore. I'll just write down what class I mean. And then once I've stated the theorem, I'll tell you what that symbol actually means. So I'm going to write down this symbol. I'll tell you what it means in a minute. So let gamma belong to this class of groups that as of now just looks like L, H, F, phi, A for any fixed commutative ring A of finite global dimension T. Then, firstly, the Gorenstein cohomological dimension of gamma exactly equals the projective dimension of B gamma A. And let's call this common quantity theta. And you come down here, you have the finitistic dimension of A gamma being equal to the SILP of A gamma being equal to the splee of A gamma. Remember, SILP means supremum over the injective dimension of all projective A gamma modules, and splee means supremum over the projective dimension of all injective A gamma modules, equal to K A gamma. Let's say, write like this. And this common quantity falls between theta and theta plus T. Results like similar looking to this existed before my result came along, but as I said, I mean, this is what I was able to prove. And the reason why I brought up conjecture A right before stating this result is it turns out, well, let me do it separately. So detour within a detour maybe, but so there is a conjecture B that I made separately. So the conjecture that I made was for any, so this is entirely due to me. For any group gamma and any commutative ring A of finite global dimension, I said that the projective dimension of B gamma A should be exactly equal to the Gorenstein cohomological dimension of the group. And it turns out, and I wasn't aware of this when I formulated this conjecture, that conjecture A is actually stronger than conjecture B. I don't know if it's strictly stronger, but conjecture A implies conjecture B. So conjecture A, which says that Gorenstein projectives, if the class of Gorenstein projectives is equal to the class of Benson's cofibrants, implies my conjecture that this happens. I guess I should call this a result, but this is really not that difficult to prove. So that is why this conjecture is useful, because I was able to prove, building on some work that had already been done, that conjecture A holds for groups here. And because of this implication, I was then able to get that for groups here, this equality is present. So now I think I should define what I mean by this class of groups. And once I have done that, I think I will have enough to give you the generation result on derived categories. Right. So the class of groups that I keep on mentioning, to get there, I need to first define two things. It's not a straight line, I'm sorry. Is it straight? Let's say it's straight. So first thing is Kropholler's hierarchy, named after Peter Kropholler. It's not that, this isn't like ancient, like Peter is 65 now. So it's not that old. And number two is groups of type phi. Type phi groups. So they were introduced over Z by Olympia Taleli, whom I've mentioned before. And I believe that paper is from 2008. And Kropholler's hierarchy were introduced in the 90s by Peter Kropholler, 94, I want to say. Right. So first of all, let me define type phi groups, because it's somewhat easier to define than Kropholler's hierarchy, simpler to define than Kropholler's hierarchy. So I say, let A be a fixed commutative ring, again of, well, actually I don't need finite global dimension, just a fixed commutative ring. Then I say a group gamma is of type phi, denoted by this symbol. This symbol was sort of invented by me. So gamma is in F phi A if for any, it's if and only if, like I'm defining, for any A gamma module M, the following are equivalent. So number one, the projective dimension of M is finite. And number two, the projective dimension of M is finite over all finite subgroups. So what you're seeing here is actually quite a running theme in the study of like the cohomology of infinite discrete groups in general. Like we find it easier in many cases to study things at the level of finite groups or finite subgroups, and then if possible, to extrapolate information from there to the big overgroup. So what's happening here is exactly that. So I'm saying if this is the case, that for any module M, whenever M has finite projective dimension over all finite subgroups, it must have finite projective dimension of the big group. I call my group to be of type phi. So some examples and some non-examples. Let me just do it quickly. So examples are, well, groups, let's say, of finite virtual cohomological dimension, groups acting on trees with finite stabilizers, the thing is, you can't really do type phi stabilizers, like you can't iterate like that. I mean, it's a result by me, but it's actually not very difficult to show. And some non-examples are, well, let's just say free abelian group of infinite rank. And the easy way to see that the free abelian group of infinite rank is not in here is by noting that, well, not exactly noting, you have to use this fact. So type phi groups admit complete resolutions. So remember complete resolutions that I mentioned earlier? So type phi groups, okay. Type phi groups have complete resolutions. And free abelian groups of infinite rank do not have complete resolutions. It's somewhat easy to show. So that's like one way of saying that free abelian groups of infinite rank cannot be type phi. For now, remember this notation, F phi A. So, sorry, crop folder. Now let's come over to Cropola's hierarchy. What's going on here? Well, we start with a class of groups X, and then we say H0X is X, and then we say a group G, or let's say gamma, is in H alpha X for alpha any successor ordinal. I'm burning up a lot of time. If and only if gamma acts on some finite dimensional contractible complex cell complex with stabilizers in H alpha minus 1X. And if alpha is a limit ordinal, then we do the standard logician's trick and say H alpha X is the union over all H beta X. Well, beta is strictly smaller than alpha. And we say LHX is the class of all groups that are locally in HX, as in all of whose finitely generated subgroups are in HX. So now you'd see what LHF alpha A means. So LHF alpha A means that you do just this construction And in place of X, you take the class of type phi groups, F alpha A. And that's what I had in my result, LHF alpha A. And the thing is, for a long time, all over the literature, people were working with LHF groups, and it wasn't known whether F type phi groups were definitely in LHF. Although, like, there's a conjecture that they should be for A Z, but A Z. But anyway, since I've used up a lot of time, let me just go to my first generation result for triangulated categories. So let me do this. So I want to look at D mod A gamma, where gamma is LHF phi A with some fixed commutative A of finite global dimension. So the interest in this question of generating D in the derived unbounded category comes from a paper that Jeremy Ricard wrote recently. And that paper shows that, so this is a result due to Ricard. Let me use. So Ricard shows, when the talk was, I think it's 2018. I mean, I attended a talk where he unveiled this, but that talk was in 2017. Anyway, Jeremy Ricard. And the result says that if R is a finite dimensional algebra over a field, so for such finite dimensional algebras, there is a conjecture that the finitistic dimension has to be finite at all times. What Jeremy Ricard showed that if you look at the derived unbounded category, and if you have that the injectives generate the derived unbounded category, what it means is, so in the derived unbounded category, you look at the class of injective modules, and you look at those injective modules as complexes concentrated in degree 0. Again, a standard thing to do. And then you look at the smallest localizing subcategory containing that class of objects in the derived unbounded category. So localizing subcategory means the smallest triangulated subcategory of D mod R containing the injectives. I mean, well, localizing subcategory means triangulated subcategory containing injectives, but sorry, triangulated subcategory closed under coproducts. That is the definition of localizing subcategory. So in this case, I mean, so generation means smallest triangulated subcategory of D mod R containing injectives that is closed under arbitrary coproducts. So I'm just going to use the direct sum symbol. So he showed that if this happens, then the finitistic dimension of R is finite. As in other words, the finitistic dimension conjecture holds for this finite dimensional algebra R. But we are not working with finite dimensional algebras. We're working with infinite groups and their group algebras. So my result here is that, remember this setting. So gamma is in LHF phi A. So my result is that if the finitistic dimension of A gamma is finite, then the injectives generate the derived unbounded category, as in the other way around. Of course, for the finite dimensional algebras case, it is not known whether there are any finite dimensional algebras for which the injective generation property fails. So it could be true that that this guy, so this implication here is actually an equivalence, but we don't know that. So how do I prove this using cohomological invariance? Well, we know from my result earlier, we know that the fin-dim coincides with spli. In this case, we know that. We know if the fin-dim is finite, That means spli is finite. So this means what? This means every projective module is quasi-isomorphic in the derived category to a bounded complex of injectives. I'm sorry. SILP. I need SILP. Yeah, every projective module has finite injective dimension. And it's SILP. Yeah, every project. Yeah, bounded complex of injectives. What do I do? So it is known that if you have a bounded complex of injectives, okay, now let me write it like this. Then the smallest localizing subcategory containing the projectives is contained within the smallest localizing subcategory containing bounded complexes of injectives. Actually, we don't even need smallest localizing subcategory. Smallest triangulated subcategory containing the projectives is in the smallest triangular subcategory containing this. And it is very easy to show that since we're dealing with bounded complexes here, this guy is actually exactly equal to the smallest localizing subcategory containing the injectives. But the smallest localizing subcategory containing the projectives is always the whole thing. And that can be proved based on two facts. One, every module has complete projective resolutions. So every module is quasi-isomorphic in the derived unbounded category to a right-bounded complex of projectives. And from there, using the fact that you can write any complex as the homotopy co-limit of its good truncations, or in other words, the canonical truncations, and the fact that localizing subcategories are closed under homotopy co-limits, it is very straightforward to show that, and it is well known actually, that the projectives generate the derived unbounded category, as in the smallest localizing subcategory containing the projectives is the whole derived unbounded category. So if this happens, of course, we have this equality. I mean, of course, there is nothing fancy going on here. We are just making use of the fact that findim finite implies SILP finite. So this is a result that is getting published this year, but it's basically a direct corollary of what I did last year. I didn't know it when I wrote that paper. So this is the first generation result of involving triangulated categories that I wanted to show you. The second one involves a stable category. And so I started at 8 past. So I have 4 minutes left. Is that right? Yeah. So to get there quickly, I want to first define what stab is, the big stable category. So gamma is any group that admits complete resolutions over A, and A is of course a commutative ring, finite global dimension. I'm just going to say that this category has objects, has as objects the normal modules, and the morphisms, the arrows, are given in the following way. So between M and N is given by the X hat 0 group. So what is X hat 0? Well, to get there, we need to do first this thing. So when I write hom underbar Mn, I mean all Mn arrows quotiented by all arrows that factor through projective. Factor through a projective module. For finite groups, this is the hom set in the stable category. But here, we first define this guy, X hat R over any ring Mn. It's defined in the following way. It's limit over I hat R. Then I do syzygy I plus R. I'm sorry, I'm rushing it a bit. So I want to say this is due to Benson, but this work also appears in Mislin's papers and some other people. Guido Mislin, that is. So now you see what I mean by x hat 0. So x hat R is given like this. So this is big step, and small step is something that I consider. This guy is the smallest triangulated subcategory of big step containing all modules that are of type F infinity. In other words, it means containing all modules. So it's called type F infinity. So type F infinity, the module category. So that means modules with projective resolutions. Okay, modules. Okay, I should not with. I should write modules that admit a projective resolution by finitely generated projectives. Again, I'm in the abelian module category, not in the stable category. So I look at these modules that have projective resolutions with finitely generated projectives. Then I look at the smallest triangulated subcategory containing them in the big step. So it turns out that you can show that I don't think I'll be able to show the proof. This paper is not out yet. I mean, it is coming out in the communications and algebra. Yeah, the DOI is available, but I don't have the page numbers here. So I'll just end with this. So it turns out that any module, or let's say any object in small step, so I need this extra condition, LHF. Gamma is an LHF, not LHF phi A, just LHF. It's a huge class. There's only one group that is known to reside outside of LHF. It's called the Thomson's group. Anyway, so any object in step, small step, is in the smallest thick subcategory. So thick subcategory means triangulated subcategory closed under summands of big step containing a class of modules called basic modules. I'm not going to show you how to prove this, but to use this, to prove this, we have to use that old thing, that the class of Gorenstein modules, Gorenstein projectives and Gorenstein projectives and cofibrants are the same over LHF groups. Teleli Dembejuri proved it over Z, but the same proof sort of works over A in a way, yeah. So what are basic modules? I'll tell you what basic modules are, and I'll end my talk exactly there. So basic modules are modules. So when I say modules, I'm talking about A gamma modules, of course, are modules induced up from some finite subgroup so some module, okay, wait a second. So I'm inducing up a module from finite subgroup. So what is that thing that I'm inducing up? So it has to be cofibrant, as in Benson's cofibrant, and it has to be completely finitary. I'll tell you what that means. So completely finitary means, so M is completely finitary if X hat star, this guy, commutes with filtered colimits. It's very similar to the definition of compact objects. So I'm looking at modules that are completely finitary, like this, and cofibrant over finite subgroups, and I'm inducing them up to the big group. And so that way I get a class of modules over the big group, and look at the smallest thick subcategory in the big stable category containing that class. And the result is any object in the small stable category is in there. So this is the second generation result. And the way I'm using an invariant is by using this result, because as I showed you earlier, this result is actually connected to the behavior of the two invariants that are involved here, the Gorenstein cohomological dimension and the projective dimension of that B gamma A module. Anyway, thank you for your attention. Yeah, thank you.
Okay, thank you very much. So are there any questions? Let me see. Okay, that's a clapping hand.
Okay, I have one. So you briefly mentioned the Thomson group in this last. Could you elaborate on that?
So Thomson's group F is not in LHF and is also not in LHF phi Z. So elaborate as in what is the Thomson's group?
No, that we know H, no, but
you mean why is it not in there?
No, that no, sure, yeah, I mean.
So the it has infinite. So basically, it is a group of type F by infinity, as in the trivial module admits complete resolution by finite generate projectives. And there is a result which says that if a module is of type F by infinity, I hope I'm getting this right. But anyway, it's not my result. So if I'm getting it wrong, I won't feel bad. So there is a result that says that if M is of type F by infinity, as in there is a projective resolution of M with finitely generated projectives. So M, let's say M is an A gamma module. And gamma is in LHF. And A is any ring, I think. I don't even need finite global dimension, any commutative ring. So there is a result that if this happens, and if gamma is already in here, then the following two things are equivalent, that the projective dimension, much like the definition of type phi groups, projective dimension of M being finite has to be equivalent to the projective dimension of M being finite over all finite subgroups. And so when we are working with the Thomson group, if Thomson's group is in LHF, then the trivial module has to be, so we know the trivial module is of type F infinity, basically. Yeah. And we know from there that this condition has to be true. The cohomological dimension, yeah, so the PDAGA being finite for all G finite will be true, but it cannot have, I mean, PDA gamma A cannot be finite, as in the cohomological dimension cannot be finite because it contains infinite free abelian groups of infinite rank. I think I said it right. I mean, I might have got some of the details. Yeah, this is a result due to Krophola in the very same paper where he introduced the hierarchy.
Okay.
Yeah. And actually, you don't even need LHF here. You can have LHX for any class X. And then instead of saying finite subgroups, you have to say subgroups belonging to that class. As long as that class is, I think, a subgroup closed and conjugation closed or something.
Okay.
Yeah, I think, oh, sorry, I think it is also torsion free, this group. Yeah, it's torsion free.
Mhm.
And that's why we have this second condition holding. Did I say it wrong or just the other way? I think, yeah, that's
Okay, thank you. Are there any more questions? Okay, so it seems it's all. Okay, so thank you very much, Rudradip, for this talk.
yeah, thank you. Thank you for having me.
Yeah, thank you.
Okay.
Yeah, thank you, Noah.